April 2020 semester ICT 6900 Special Topics in ICT Advanced Machine Learning এর lecture 9 এ সবাইকে আমন্ত্রণ জানাচ্ছি। Today's topic is Dimensionality Reduction Principal Component Analysis PCA, and this technique is another algorithm for unsupervised learning. We have covered in the last lecture one of the algorithm of unsupervised learning, that is K-means algorithm, and today we'll discuss another algorithm which is called dimensionality reduction. And this is a very important topic because when the data becomes very huge, then it is required to reduce the data. And this reduction not only actually reduce the disk space, that means storage space, rather than it also speed up the algorithm. So let us see how this is defined and what is the motivation against this algorithm. First motivation is data compression. When you use the dimensional reduction, the data become compressed. Let us see an example of this plot where among the number of features, let us take two features, x1 in centimeter and x2 in inches. And these are two same thing but in different units, same distance. That means this is a distance, x1 is also distance, x2 is also distance, but they are in units are different, centimeter and inches. And these are certainly redundant data. So instead of two data, we can represent the distance by a single data. And it may happen in the practical life because when the number of features of a data set becomes high, we may collect the data by different groups. For example, you have a 1000 features data set and you ask one group to collect 300 data, one group may collect 200 data, other may collect 500 data. So total 1000 data, and among this data there is a possibility of such redundancy. So we can remove this redundancy by reducing the similar data or very closely related data. For example, these points can be joined by a line, which line is close approximity to the data, and the corresponding value on this line may represent the distance instead of separately x1 and x2. We may call z is a distance and z may be the distance along this line. And this can be applied for some other purpose. For example, in a helicopter pilot, you can have two sets of data. One is pilot skill, other is pilot enjoyment. And combining these two set of data, you may call another data which is called aptitude. So you may replace these two data, that means pilot skill and pilot enjoyment, into a single data called aptitude. And this data is nothing but the data on this line, which is corresponds to the other data. So let us see how to convert two data into single data, 1D data, two-dimensional data into single dimensional data. So let us plot the same data set in colored form. So in the colored form, you can see the same set of data, and if you plot a best line, on that line represent very close to the data. In the previous case and in the present diagram, we can see x1 in centimeter and x2 in inches. Although They are related by a single constant, which is 2.54, but because of the rounding error, x1 may be close to the round to the centimeter. You have removed the decimal part of the centimeter, and also x2 is close to the complete inches. We have removed the decimal, so the point may lie in different position because of this rounding error. And this data set, if you project each and every data, project the data over the this brown line, the data can be represented by a single dimension z. And in this example, that means given data was x1 and x superscript 1 is the first data, and it has got two components, x1 and x2. And these two-dimensional data can be represented by z1. Similarly, x2, which has got two components, you can convert into z2. So x1 is a two-dimensional data, but z1 is single dimensional or just real number. Similarly, x2 is also two-dimensional, and z2 is a single dimensional or just real number. So similarly, all the data set that you have up to xm, all are two-dimensional data, and corresponding z is a real number or single dimensional. So in this way, you can convert two-dimensional data into a single dimensional data. So let us see the similar feelings for converting 3D into 2D. So this is a plot of a number of points, maybe 1,000 point, and you want to convert this data to, say, for example, 100 points. So what we'll do, you will have a plane. How to get the plane we'll discuss later on. What is the optimum position of the plane? How to find out that plane, we will discuss that one. But let us say this is the plane where all the projected data you can have, and that data will give you the minimum error after projection. So after projection, the data may be on the same plane, and it might have two axes, z1 and z2, and each point on this plane is represented by two number. One is on the zx, z1 number, another is z2 number. So if you plot in two-dimensional plane, the plot will be like this. So each and every point has now got two values, z1 and z2, instead of original data where every point has got three values, x1, x2, and x3. But if you project all the data in single plane, not on the x-axis, xy plane, not in the yz plane, it is arbitrary plane, but a straight plane. So in the plane, if you project all the data, it may look like this. And you can convert this x data, that means x superscript 1 up to x superscript m, into z superscript 1 up to z superscript m. So this is how the 3D to 2D conversion is meant. Let us see on the real plot, say in the MATLAB or in the Octave. You can plot your data in the 3D, and you have also function to project all the data in a single plane. Let us say after you take the projection of all the data, it look like this. These points are in a single plane. If you see in two-dimensional form, the data are this data. That means these data are projected data on the original data. And projection on what? Projection on a plane. Which plane is optimum plane? We have not defined, we have not discussed about how to obtain that plane, but there is a technique to find out the optimum plane. That means plane where the projection error will be minimum. We'll talk about what is projection error and how to find out that plane, or in case of 2D to 1D, how to find out the line. And it's not only 2D to 1D or 3D to 2D, it's all actually from n number of dimension to k number of dimension. N could be any number, k could be any number. So depending on your requirement, you will fix up what is the k. There is a technique how to find out the k. K means the number of dimension in the reduced plane. Let us talk about motivation number 2, data visualization. If the number of features in a data set is large, if the number of features in a data set is large, it is difficult to visualize the pattern of the data. Let us take an example. This is the various data of a country, and that represents different type of information for a country. For example, GDP, the total GDP of the country, per capita GDP, that means GDP per person, Human Development Index, then life expectancy, poverty index, mean household income, etc. So let us say there are the features are termed as x1, x2, x3, x4, x5, x6, and so on. So there may be a 50 number of features in a certain row, that means features for a country. And there are a lot of countries in the world. So this is a big data set, and being a multiple features, that means 50 number of features, it is not possible to visualize by graphical plot. That's why if you can dimensionally reduce this data, then it may be possible to visualize the pattern for a certain data set. For example, if I reduce the data from 50 dimension to 2 dimension, and let us say the variables are z1 and z2, combining the given data, we can find out two variables z1 and z2 for each and every country. This particular z1, z2 may not have any physical meaning, but these are obtained from the given data, so they represent the given data. So if we can plot this data, then we can visualize the different relative difference between the countries. And let us say it is a two-dimensional array, that means the number of features is 2. So that's why if we plot the z1 and z2, we'll have this plot. Each and every point represents some country. For example, USA, Singapore is shown, and all other points actually for a country. And let us say the Z1 axis is representative of country size in terms of GDP, and Z2 axis may be per person GDP, economic growth. So this is not actually directly per person GDP or country GDP. It's a representation of per person GDP and representation of country GDP. Because Z1 and Z2 actually combined information of all the 50 information of a certain country. Although we have dimension reduced, but each and every point has two values. We can easily say that Singapore has got high country GDP and high per person GDP, whereas USA also has got high country GDP is more than Singapore, but the per person GDP is slightly less because Singapore has got less number of people. So each and every point, for example, this point, whatever country it represents, must have poor GDP and poor economic growth. That's why this data is visually representative. You can see the data. Previously, you cannot see the data because 50 number of data you cannot plot. So this is how these data visualization you can obtain using your dimensional reduction algorithm. So one point is the reduction of the data set, that means reducing the storage capacity. And the second motivation is you can visualize the data. if you can dimensionally reduce the data. Let us discuss about problem formulation for PCA. So how to formalize the problem of converting a certain dimension of data into a lower dimension of data. So PCA is one of the method. It's not the only method. So principal component analysis is based on certain principle. So let us say these are the points that is given where x1, x2 are the features. So number of features is 2 and two-dimensional data we want to convert into a single dimension or singular data. So this is the fitted line, and the objective of finding the line is that the projection distance are shown by the red color line. These lines are the error between the line, the point on the line and the actual point. So this will call projection error. And if the summation of the square of this projection error is minimum, then we call the line is the best line. So for different line, the projected distances or projection error may be different. For example, if you have a line like this green one, and if we take projection, and the projection error will be like this. And if you take the square of this projection distances or the errors, then it will be much higher than the previous line. So this line, the previous line, that means the blue line, we call it the best line. So this is the main principle of finding a single dimensional vector, the single vector on which the projection will be made. So these are the points on the line for the second case. That means when green line is treated as the direction of the projection, but it's not the best line. Similarly, if you find out the principle would be to reduce from two dimension to one dimension is find a direction of vector. That means this red vector, find a direction onto which to project the data so as to minimize the projection error. There may be some other line, some other direction vector, and this vector may be the best vector because the projection error from the given point onto the direction vector is the error, we call it error, and the square of the error is minimum. Is let us call it E1, and even it is minus E1, the same thing happens. So it doesn't matter about the direction. The line is the important parameter. That means either it can be U1 or it can be minus U1, whatever may be the direction, ultimately the projection of the line, of the point on the line, the error should be minimum. So in case of n-dimensional vector, that means the points are n-dimensional, and if you want to reduce into k dimension, find the k vector. Like the single vector u1, you have to now find out u1, u2, u3 up to uk. And the surface that is constituted by these vectors. And we have to find out the projection error of the given data, which is n-dimensional data, and the projection onto that surface constituted by u1, u2, u3 up to uk, and so as to minimize the projection error. So it is understandable by two-dimensional vector. If you have you can assume a plane where the two vectors u1, u2 are the two vectors, and we have to find out the two vector u1, u2 by which you can constitute a plane, and this plane will be the surface on which the projection will be made. If the total error, that means summation of error square, is minimum for this plane, then we call u1, u2 is the vector that is reduced from three vectors. One vector was in the x1 direction, other was in the x2 direction, other vector was in the x3 direction. But now the two vectors u1, u2 constitute a plane on which the projection is made. So you call it k equal to 2. Similarly, for k equal to small k, you cannot that you cannot visualize the projection like this one, but the principle is same. So if you want to convert a n-dimensional vector into k-dimensional vector, what you have to do, you have to find out the k number of vectors like this one. We have found the two vectors u1 and u2. So this is the problem formulation for PCA. So what is the error? Error is actually for this particular point, if you take the projection, the yellow line is the projection vector, the the not vector, the distance, actually the distance between the line onto the surface, and this is your point on which you have projected. So this point is the point on the surface, and this point is above the surface. You have to draw a perpendicular line from the point onto the surface, so you'll get the projected point. And the error between these 2 points is the measure of error and for each and every point you have to find out the distances and take the square, and you have to minimize that distance. So by this you will get u1 and u2. So sometimes, since it deals with the error, sometimes people are confused whether it is similar to linear regression. No, this is not linear regression, because in case of linear regression, the left figure shows the principle of linear regression. In this case, the x1 is given for a single variable case, x1 is given for different point, and for that points y is also given. So what we'll do, we find out the straight line on which the error between the point onto the line, not projection, this straight line, the vertical line, actually these vertical distances are the measure of error. But ex- in case of PCA, the straight line is found out and the error is also found out, but this error is not vertical error, rather it's a perpendicular error from this point onto the surface. So these distances you have to calculate the total square of the errors, and then you have to find out the, so both x1 and x2 are considered for the calculation of errors. But in case of the linear regression, the x1 is the variable, y1, y are the known values. So this y is computed with the given x. So given x1, we calculate the actual point, this point, and then we determine the error. But in this case, the x1, x2 both are important, because this is the point where x1, x2 lies, and from that point you have to find out the perpendicular distance, not vertical distance. So that is the difference between PCA and linear regression. In case of two-dimensional case, when we convert the three-dimensional data into two-dimensional data, all the this point has is all the x's, that means x1, x2, x3. All the x's are important, and we have to minimize the distance between that point onto the surface of the surface of the reduced plane. So this plane is the reduced plane, and on which you have to calculate the surface. So PCA is never is similar to the linear regression, although there is a cosmetic similarity, but practically it's not similar. The principal component analysis and the algorithm for PCA. The first step is data pre-processing. As we have discussed in case of supervised learning, the same technique we have to apply for pre-processing the data. So the steps are, first of all, you have training set like x1, x2 up to xm, and you have to do the pre-processing by feature scaling and mean normalization. So for that matter, you have to calculate the mean mu j, and that mean you have to subtract from each xj so that the average is always zero. And if the different features on different scales, that means if there are n number of features and those are in different scale, for example, x1 is size of the house, x2 is the number of bedrooms. So in that case, you have to scale down or scale up to a certain range that all are in comparable range. The technique is very similar. For example, xj should be replaced by xj minus mu j divided by sj. Sj is the size. So size of that or range of that particular features. For example, if it is a size of house and the different data says that house ranges from 0 to 2000 square feet, then Sj should be 2000. That means the data ultimately the xi will be within range of -1 to +1 or -0.5 to +0.5. Reduce 2D data to 1D data, and we have discussed that in the previous slide. And in that particular example, we showed that if xi is in the second order, the order is 2, for example, all the data. And if you want to convert this data into a single dimension, then the conversion will be z. x1 will be converted to z1, x2 will be converted to z2, and zi, that means all z, will be a real number. That means the order will be 1. In case of three-dimensional data, if you want to convert this three-dimensional data into two-dimension, you have to have a two vector, u1 and u2, and that two vector will constitute a plane, and you have to project all data on that plane. And xi is in the order of 3, but zi will be in the order of 2. That means z will have two components. One is z1 and z2. Z1 is the component which is corresponding to the U1 axis, and Z2 is the component which correspond to the U2 axis. So this is the technique, but we didn't discuss about how to find out the U. In case of 2 to 1, U1. In case of 3 to 2, you need two vector, U1 and U2. If the number of features or number of elements in a X is n number of feature, and you want to convert into k number of feature, that means k dimensional data. The n dimensional data, if you want to convert to k dimensional data, you have to have k number of vectors, u1, u2, u3 up to uk. So mathematically, we can prove how to determine how the formula is to derive, but we are not interested in the derivation rather than how to calculate the systematic approach of calculating u from given the data in n dimension. Let us discuss that technique. The technique says if you want to reduce data from n dimension to k dimension, first of all you have to calculate the covariance matrix. Covariance matrix is determined by sigma. This symbol actually capital sigma. This is very similar to the summation sign, but it's not summation. The left hand side is a sigma, and you have to multiply xi with xi transpose, and then you have to sum them together, and the all multiplication results has to be summed for m number of examples, and then take average of 1 over m, then you will get the sigma. This is called covariance matrix. Once you get the covariance matrix, then you have to calculate eigenvector of matrix sigma. And this is given by this equation USV, this particular V output is given by a function called SVD. So this function you have to apply over sigma, which is calculated from this equation. And if you see that abbreviation SVD, it's actually single value decomposition. And we are not going into detail of the how this SVD works. Rather than we'll use this SVD, and for that matter we have to calculate the sigma. This is the symbol for sigma, and xi is n multiplied by 1. That means n by 1 matrix. There are n number of features and single column. So n by 1 matrix, and if you take transpose, that matrix is 1 by n. If you multiply them together for a single I, that means one example, then the dimension will be n by n. So for one I, that means I equal to 1, for example, you will get 1 n by n matrix. For second I, you will have another n by n matrix, and so on. You will have m number of n by 1 matrix. If you sum them together, and since they are all are of equal dimension, you can sum element by element, and ultimately you will get a total value of n by n matrix, and that you have to divide by m or multiply it by 1 by m to get the sigma. Once you get the sigma, you apply that sigma into built-in function. This is for Octave, and MATLAB also have similar function, and other language also have function like that. Ultimately you get USV. For the time being, we are interested on U. You remember we talked about U matrix, sorry, U vector, U1, U2, U3 up to UK, and this actually is n by n matrix, and sigma is n by n matrix, and E is also n by n matrix. If you see the SVD, this single value decomposition function, there is another function, eigenvalue function, eigenvector, eigen, and similarly sigma. So you can use either of these two functions for calculating U, and U is actually this kind of matrix. Although you have n number of column matrix, n number of column matrix, if we are interested on the only k numbers, we have to take k number of columns to get U1 up to UK. So U is the order of n by n, and this n by n matrix among the n column, you just take the k number of columns. And if you take k number of columns, this first k number of columns, you will get a matrix, and that name is U reduce, U1 to UK. That means the steps is you have to find the SVD function output, and one of the output is U, this U, and you take the reduced part of U, which is consisting of first k number of columns. So size of this matrix will be n by k, n number of your row and k number of columns. And if you take transpose of this matrix, then it will be k by n dimensional matrix. So these two matrices will be required for our further processing. If we summarize our steps, first of all, after mean normalization, ensure every feature has zero mean, and optionally feature scaling. Optionally means you may not need feature scaling. If the all values are within the comparable range, then you do not need to have the scaling part of the preprocessing. Then calculate sigma and calculate USV, and this is the matrix implementation. If you want to take the summation, it's okay, but you can avoid the long calculation process due to this summation. You can obtain the same result with vector calculation. For example, x is defined by this kind of matrix where x1 transpose forms a row, x2 transpose forms another row. Similarly, xm transpose form another row. So there are m number of row and n number of column, m by n. And if you take transpose of x, that will be just n by m number of column. So if you multiply x transpose with x, and then it will be same result of this summation. So it's a very straightforward. You just calculate by this matrix multiplication, vector multiplication, and you'll get the sigma. This sigma you pass to the SVD and you get this. If I do the dimensional analysis, then this x prime is n by m and x is m by n. So multiplication will be n by n. So sigma is n by n matrix. And then you have to calculate U reduce. U reduce means the number of column will be 1 to k. You take all the rows, but number of column is 1 to k. And you reduce if you multiply a single example, you will get single z. That means if the x is n dimension, then z will have k dimensions. That means n number of features in x will be converted into k number of features in z. So in this case, if you take the dimension analysis, U reduce transpose is equal to k by n and x is your n by 1. So if you multiply them together, you will get k by 1. So x is converting into z. X is n by 1 matrix, a single column, because this is actually a single example, and z will be k by 1. So this is again a column matrix, but number of features is k. So we are converting n features vector with a k feature vector. Now let us discuss how to choose the value of k, number of principal components. The value of k means, as we mentioned in the earlier slides, the n dimensional data will be changed to k dimensional data. And this k, how to determine k, whether k should be 2, k should be 3, or etc. So the steps that we have to follow in determining the value of k are to find out two values of the expression. One expression is called average squared projection error, and other is total variation in the data. The first expression is the error square. What is the error? It is the actual x, that means the given value, minus the value that is projection on the surface of the reduced vector. That means the surface, if it is a two-dimensional surface, then that in that plane, what is the projection of xi? So xi minus xi approximate, that will give you the error, and that error square summation over 1 to m and average over m, that will give you the total projection error. Similarly, the other expression is total variation in data. That is the all the values of the x, that means the distance of the vector or length of the vector square, and that is summation again over 1 to m and then divided by m. So these two quantity, if you take ratio of these two quantities, and if it is less than a certain small percentage, let us say it is 1%, then we call the k is attained. That means you choose a k, and for that k determine this ratio, and you compare this ratio with a given value, that means your chosen value. When it is said that it is less than equal to 1, that means, in other words, we will call it 99% variance is retained. What does it mean? It means that if, for example, if there is no error in the numerator, if there is no error, it means that this quantity will be 0. That means 100% variance is written. That means no variation in the actual data and the projected data. But we expect that it could be some error, and that error should not be more than a small value. If it is compared with 1%, then we call it 99%. If it is 5%, then we call it 95% variance is written. So the 95 to 99 is the typical value of comparing this. So for example, if you choose k equal to 1 and then k equal to 2, k equal to 3, k equal to 4, and you calculate this expression, and if you see the variation is retained for a is obtained for certain value of k, then you stop there. For example, if for certain example you obtain this limit when k equal to 17, so you choose k equal to 17 for that problem. The same result you can obtain in another way, which is simplest way. You remember in our earlier slide we have defined that we have to find out the single value decomposition, and that is given by this expression where u, s and v are obtained from this function. And use of u we have already discussed. Now s vector is actually a diagonal vector where s11, s22, etc. are non-zero value other than the diagonal elements all are 0. And for determining this ratio, there is another way, and the way is to find out this expression. This expression says 1 minus I equal to 1 to k SII. That means the first k diagonal elements, you take the summation, and the all diagonal elements, you take another summation. This ratio, 1 minus this ratio, is the expression, the value of the expression is same as this expression. In other words, this expression is subtracted from 1 should be around 0.95 to 0.99. So this is the simplest way to check whether the smallest value of k is obtained. So you increase the k every time you will calculate this ratio, and if it is more than 0.99, then you stop there and k value is obtained. If this value is greater than or equal to say 0.95, then we call 95 variance is retained. So it is our choice how close we want the projected data to the actual data. So we'll decide accordingly. The normal value is 0.95 to 0.99. Until now, we have discussed how to convert a high dimension data to a low dimensional data. That means reduction of dimension. Now let us say once you have reduced the dimension, if you want to reconstruct, that means you want to go back to the original data, whether you can do that. Say for example, in case of two-dimensional data, that is the data like this, what we do, we find the z, that means the 2 to 1 dimension, z we obtained by this formula, u reduced transpose multiplied by x. And how to get the u reduced we discussed when you discussed about your SVD function. So the SVD function you will get u, and if you want to keep the k dimension, then you keep the k number of columns of the u, and that is termed as u reduced. And if you transpose that one, that is called u reduced transpose. You multiplied that u reduced transpose with a single example, that will give you the converted single example, corresponding single example. So if you work out the dimension, this u reduced transpose k by n, and x is n by 1, so z is also k by 1. So n by 1 matrix, that means n dimensional vector x is converted into k dimensional vector of z. And in case of z, in this example, z is a real number where x is a two-dimensional number. And if you want to go back in the other way, the formula is u reduce multiplied by z, and that will give you the x approximation. That means projected value, not the actual value. And since we have computed this k-dimensional vector by choosing a very small number of error, that means a high variance of the data, so x approximation is actually close to the x. So if I calculate the f of x approximate, the data will look like the diagram shown in there. And if you see the dimensional analysis, the u reduce is n by k and z is k by 1, so the multiplication is n by 1. That means the converted data is again retained back into the original data. So this is the way how you reconstruct from the compressed representation. Let us now discuss about the application of PCA. So if you apply PCA in the supervised learning algorithm, sometime it will speed up and it is necessary in some applications. In the supervised learning application, the data sets are like this: x1, y1, x2, y2, up to xm, ym. Let us say you are considering an image having 100 by 100 pixel. So the data is in the order of 10,000. So this is a huge data. If you want to compress this data, for example, in the order of 1000, then you can apply PCA. So what you will do, you just extract the inputs x1, x2, x3 up to xm, and the order is 10,000. And this is now unlabeled data set because you have removed temporarily the y. Then you apply PCA and you get z1, z2, zm, and these z's are in the order of, say for example, 1000. So in that case, you apply the new training set. The given training set, you just change to Z1 Y1, Z2 Y2, Zm Ym. What is the difference? Difference is that X1, X2, etc. were in the order of 10,000 and Z1, Z2 are in the order of 1000. So if you apply logistic regression or neural network, it will be quite faster now. So after getting this new data set, we apply whatever method you want to apply. For example, if you apply the logistic regression, then the hypothesis should be like this: Hz is equal to 1 over 1 plus e to the minus theta tz. So the x will give you the z by PCA, and apply this z into this function, you get the hypothesis. That means the predicted value of y you get from there, and you can then calculate the error and modify your theta and proceed in that manner. So once you get this hypothesis, then you can test your system. So the technique is that first of all you map xi to zi through u reduce that we have already discussed, and that should be found out only on the training set. And this mapping you can apply as well for the other set, for example cross validation set, and also on the test set. In fact, the given data, first of all you 95% or 90% of that data you keep as a training set, and a certain percentage, small percentage as a cross validation set, and other remaining as a test set. So once you get the mapping, you just found out the you just apply the cross validation set, and then you see the result, and if it is satisfactory, then you proceed to apply the test. After applying the cross validation set, if the performance is not, or the result is not that accurate, then you will review the original training. And once the training set and cross validation set are giving the proper result, then you apply the test set. But the mapping you have to do on the training set. The other sets you do not involve in mapping or in reducing the dimension. So in the cross validation set and the test set, you apply directly following the hypothesis that you obtained from the training set. The next discussion point, let us summarize the application of PCA. We have seen that there are two applications. One is compression, other is visualization. In the compression, we can reduce the memory and disk space needed to store the data, and we also can speed up the learning algorithm. And both of the objective we can obtain by choosing K by percentage of variance retained. So that we have discussed already. So this is how you can apply the compression and also the visualization. If you want to visualize the system, you can reduce your system into two-dimension or three-dimensional system so that you can plot the system and you can have the feeling how the data different from one example to other example. Let us discuss about some bad use of PCA. And sometimes people use this PCA to avoid overfitting. They use ZI instead of XI to reduce the number of features, and the number of features may be K, which is less than N. Thus, the fewer features, less like to overfit. This is their intuition that if the features can be reduced, the overfitting problem can be avoided. But this is bad because the method might work okay, but is not good way to address the overfitting. So, suggestion is use regularization instead of this application applying PCA. And you remember the regularization is given by this term, addition of this term. And if you remember the particular topic we discussed in the supervised learning, and in case of supervised learning, each x is related to the y, and the PCA is not considering the y, only the x. It takes out the x and then it reduced to z, and that's why the overfitting problem may not be removed if we use PCA rather than you are suggested to use regularization. And PCA is sometimes used where it should not be. And normally, the design algorithm, people takes the xi, yi, then run PCA to reduce the xi to dimension in dimension to get zi, and train the logistic regression and also test on the test set. So these are the steps people normally follow. But the suggestion is, how about doing the whole thing without using PCA? And before implementing PCA, first try running whatever you want to do with the original or raw data XI. For example, you want to apply neural network or logistic regression, you apply with your raw data, original data. Don't reduce the data first of all. Only if that does not do what you mean, what you want, then implement PCA and consider using SEDA. For example, if disk space is very limited, then you apply PC, or you want to visualize the data, then you use PC. Otherwise, in most of the cases, your raw data will work. That's why suggestion is don't apply PCA right way. You try first with the original data in an algorithm, and then if the problem arises, then use PCA. That's all on the PCA, and it is a very useful algorithm for unsupervised learning, and you will find a lot of application in practical life. Thank you very much.